Good afternoon, everyone. Thank you very much for your patience. Thank you for being here and for being online. This is Linda from Wits, and I'm very excited to introduce the speaker. That is Dr. Jun Cowan. That is an experienced structural geologist, and at the moment is consultant and is based in Fremantle, in Western Australia. He's actually the conceptual founder of a common or a very popular software for body modeling that is Leapfrog, and actually has fun in developing many more applications. And he has also fun in teaching body modeling, structural geologies, and especially connected youth. We have been very lucky these 2 days that he was spent a couple of 2 days, 1.5 days session with the geology honor class, and now he has a presentation for us. Thank you very much.
Thank you so much, Linda, for the invitation to come here and speak to you and go through the workshop for 1.5 days. It's been absolutely fantastic. You guys are heroes, very good. No experience with geological modeling, but you were just great. Okay, so I'm going to have a very long talk, about 260 slides, very detailed, lots of small text. Well, no, I'm just joking. I have an extremely long introduction. It's going to take up half of the slideshow, but at the end of it, I'll have an extremely short scientific method that everyone can use. And I'm going to then, I have a rapid fire cancellation of established forward deposit models, because at the end of the talk, I'll have to give you what mineral deposits really look like. So this is my introduction. You may know me from these incredible articles. Why I give geological cross-sections cold shoulder. Why gold deposits are like Tom Cruise and nothing like Justin Bieber. I don't know why that wasn't accepted in economic geology, to be honest. But I do occasionally write some articles, and this one is published in AJS with Bruce Hobbs. That's Bruce Hobbs. And he's 90 this year, quite a remarkable man. He's, some say he's the Yoda of structural geology. And of course, I'm but with, so it will be. Okay. Gosh, thanks, Robert. That's crazy. Okay, hearts look like this. What do epigenetic mineral deposits look like? And you get this. There's a whole bunch of two-dimensional cartoons. What do livers look like? They look like this, pretty detailed. What do VMS deposits look like? And it's been upgraded to three-dimensional cartoons up there. Lines look like this, and orogenic gold deposits look like this. So more of Looney Tunes cartoons. So you guys know about Gray's anatomy, right? It looks like this, has amazing detailed diagrams like this. Now, if a geologist were to make that volume, it would look like this. So there is nothing wrong with schematic drawings, right? You have the real thing, and then you have the schematic drawing right next to it. The problem is, in economic geology, you only have the schematic drawing. There's nothing real behind it. I've never seen a VMS deposit that looks like this. They look like this. I keep on looking at these things, grade distributions. So how did we get here? We have economic geology. They publish this volume every 25 years. This has over 1,000 pages, but only one 3D model of a mineral deposit. And that seems mysterious to me because all deposits are three-dimensional and we don't get any illustrations of these. This is a deposit called Kidd Creek in Canada. It's one of the largest VMS deposits in the world. This volume is huge as well. But lots of cartoons, no 3D model. So I'm going to tell you what you should not do. Okay. Read articles, memorize models, and regurgitate models, because this is rote learning. This is not real learning, right? Because you'll get replaced by AI. AI is far better at doing that, regurgitating model stuff, so much better at it. So right now we have VMS models, take your pick, but they're cartoon artists. So geology academics really don't know. You guys are going to be the first. Okay, so here is a non-geological demonstration of what I'm talking about. And I'm going to introduce the butterfly model. Okay, so this is like no deposit model, but it's about butterflies. So butterflies develop from caterpillars. Caterpillar turns into a green pupa, turns into a brown pupa. Then the butterfly comes out, dries its wings, and then flies away. These are called swallowtail butterflies. When I was a kid in Japan, my science teacher said, you need to do an experiment during the holidays. You can do anything, but you need to take notes, detailed notes. So I decided to raise a caterpillar because there was a creek right next to my house, got a caliper. I took very good care of it. I gave it the best sleeves, took it to walks, fed it regularly, met his mates at the creek, And I took detailed notes on the progress of the growth development of it. And as expected, according to the model, it turned into a pupa, a green one, and then it turned to a brown one. And I took it to school in a cage when it was brown, put it near the windowsill, and we had the science class. During the science class, someone said, hey, look at Jun's thing. The butterfly was coming out of the brown pupa. And it was drying its wings, right? And everyone rushed over and looked at it. That is amazing. So I've given you all the data that you need. Observe data and think, okay? This is not an AI image. This is me. My dad took a photograph of us because of this unusual thing. Now, what do you see that's unusual? And the first person who's going to guess can get one of these. Wing structure. Where's what? The wing structure is is what? Picture of a cross section of the fault. And it's a vertical cross section, it's not down plunge. These are down plunge projected view, and you can see the fold, this anti-fold here, and on the left-hand side of the axial plane, you can see there's a mineralization, lead and zinc mineralization, very poor on the other side. So this indicates that the mineralization had to happen after the fold, after the axial plane had formed. So this is proof that this is an epigenetic deposit. So the syngenetic model of Mount Isa is falsified. But how can you reject the syngenetic model? It's been accepted by decades. Well, that's because you can accept the charge. Okay, I'll just give you an example of this. This is a syngenetic scenario, a cartoon of fault mineralization on one side, but this is a syngenetic example. But if you take into consideration folding deformation of the strata, you might look at this is mineralized. So the yellow portion is mineralized. So it could have happened that the deposition after the deposition mineralization happened, then the folding. That's one interpretation. But if you put a fracture through there, you just don't know when the mineralization happened. It could have happened before the folding, after the folding, after the fracture. But if you have asymmetric mineralization like this, we know that mineralization in this case, it has to be after the folding, and in fact after the fracture. Is everyone okay with that? It's fairly simple. And this is another example, it's very similar to the previous. So this has to happen after the fracture. So I've come up with a little diagram that we published with Bruce. And these are the scenarios where I'm going to talk about this. Barra East is a gold field deposit. I think most of you know about saddle reefs. Saddle reefs are thought to be formed during the folding event. But if you look down at those folds, those mineralized folds, you can see the grade is non-continuous. This is the structure. Tectonic grade. Looking down, these are upright folds, and you can see, if you zoom in here, that there are what's called cross courses. This is historically they've been called cross courses, but they're basically fractures and faults. And on one side of those faults mineralized, and on the other side is very good mineralization. Sorry. Right here, very little less high grade here. So you have a whole bunch of these things. So this is the situation here, barite, gold. So you can have mineralization in the yellow portion, and that could be parallel to the axis, but they would be truncated at the ends by these fractures. And they are defined by two different axis symmetries. We went through this in class in the last few days. These axis symmetries are really important. So the one thing to remember about this is that axis symmetry is very difficult. In fact, most economic geology work concentrates, have concentrated on looking at the Wits. So looking at the fold axes, looking at sedimentary details in the Wits basin, for example. That's all associated, that's the red axis, but not the bounding symmetries. I've talked about this axis symmetry issue with Ron Reed. And in 2023, we were awarded the best economic geology paper for that year for this particular one. The point about this is that these drill holes are all the same, exactly the same. Okay? This one is just pressing a button. These ones, you have to redetermine the axis symmetry of that data set and then incorporate that into the modeling itself. So you have to know the structural symmetry of the data if you want to produce an accurate resource model. Shear zone orogenic gold is well known to model. It's produced by Simpson, 1988. This is another diagram by Groves, but essentially they're pretty much the same. The cross section of very steep reverse shears. Now, the expectation is that these things should have a horizontal continuity of grade. But when you actually look at this, and I've examined the Sigma deposit, which this model is based on, it doesn't have that pattern. It has a vertical continuity. You'd expect it to be horizontally strong. When you look at gold deposits and their grade distributions, they look like this. They're very spotty. So you have discontinuities like that. They look like what I showed you before. I think they're bounded by fractures. We know that grade continuities occur along fault hinges. We've seen that, but it was mysterious to me for a very long time why we have a fault plunge mineralization. It's very high grade, and suddenly it just ends. There's got to be a boundary. You can see that pattern here. So these are Hogan's discontinuities at the deposit scale. So I think the shear zone model of gold is wrong. The mineralization doesn't happen during shearing itself. It's actually post shearing. But what about Professor Simpson and Roberts? You have to trust the charts. The fifth deposit I looked at one area here. And I've combined two different data sets into one, published by two different people. And one thing you notice about this is this fault zone here. On one side of the fault zone, it's very high reef thickness. So this has asymmetric mineralization here. And I've reconstructed the three-dimensional shape of this. It looks like this. And you'll see that there is an asymmetry across this antiformal crest. So I think the mineralization happened after the fault. So it looks like this. It's very similar to the Mount Isa situation. So to place the model, I think, in this case, is falsified. But what about all those place research as well? Pale gold deposit in South Carolina. This is an interesting one because they thought this was post a pre-deformation mineralization. We've got data. Really, it was measurements from, and they believe that it was all falling itself. But when you look at their map, this paper, you notice something strange about this. This is the tectonic grain. So this fold is several generations of folding, I think two different generations of folding. This is the mineralization in red. You'll notice that the boundaries of the red mineralization in some places are parallel to these dikes, which are triassic. The mineralization is supposed to be weaker. So how could it be that the gold is actually bounding up against something that is triassic? You look at a cross section, it looks like that. Now you can see this space cleavage, that's S2. There's another bedding and probably S1 with it. This is the sulfide, and the sulfide is actually on one side of S2, which means that the sulfide after the S2. Another thing you'll notice is that the molybdenite vein goes right across these two fragments. And that's the molybdenite they claim to have dated. Yet the molybdenite is younger than the structural signature here. So I think this model is wrong. The mineralization is actually very late after the folding. So this is falsified. And you might ask, but how can we learn about these amazing changing structural geological skills? You can come to us. We'll be running a workshop next year. So that's great. Brett Davis. Yeah, the next one is in Perth in October as well. And also, trust you. Horn VMS deposit is in Canada. Again, this is a syngenetic, of course, it's a VMS, so that's volcanic. This is the reconstruction, it's subsea for replacement interpretation. And you'll notice that it's not to scale. Okay, this is quite common in geology. Lots of diagrams not to scale. So is this one. If you look at the map, this area, that's the deposit there. Gold bearing deposit is in red. Above that is the sulfide bearing. This one, if you look at it very carefully, there's a Proterozoic dike, this IKN. Proterozoic dike that goes right north-south. You'll notice there are little flat bits. Why is it that the sulfide is actually damming up against the dike that is Proterozoic? Okay, this was a problem in the 1930s, and they wrote, this guy Price wrote about it. This is the cross section of the horn deposit before it was mined. This is the sulfide deposit there, and across this dike, the compositions are completely different. I've just colored it so that you can clearly see the composition difference. You might have high copper over here, but low copper on the other side. So there's asymmetry across this dike. And in fact, this author concluded that the ore bodies are post-diabase. This is before they had radiometric dating, so they didn't know the age of the dike. But he was convinced that mineralization was after the dike because of this asymmetry. So I think this model of syngenetic mineralization is wrong. Actually, it's after the fracture that formed, after that folding, and then before those dikes came in. Here's an anonymous VMS from Australia. If you look at the grade, there is this boundary. And there's this step, this asymmetry in the grade. If you look at the geological map, there is no, strain separation across this fault. If you look at the mapping, it's just continuous. So that cannot be explained by some sort of faulting. So these are some of the transverse faults that come across here. So this is the mineralization, I believe, is after these faults. So after the folding and after those faults. So again, the model is falsified. This is another one. We have this little patch of mineralization, but you can see transverse structures that go across the tectonic brain. I'm just twisting around to show you this. It's a bit slow. Okay, so inside, between those boundaries, there are faults. You can actually model that. Here they are. So the mineralization is actually bounded with fault axis within that zone, but it's bounded by those vertical fractures. And this is the tectonic brain running through this way. Transverse faults going right across it. So this is a map of that area. You can see there are faults running across it, and the mineralization is actually bounded by these faults. So I don't think this is a volcanic deposit, it's actually later orogenic. Sturgeon Lake is a deposit that I looked at a long time ago when I was a master's student. This is master student. And this is supposed to be seen volcanic as well. But the problem is, in this terrain, all the rocks are falling. When you look into there are faults. So there are very tight faults. It's just that everything was parallel to each other. So this publication said that these are single volcanic faults. I asked them, what and majority of them thought that these are post-fault faults. So the mineralization is actually after the faults and fault. Rio Tinto is a very famous deposit in the Iberian Sahara Belt. It's number 2 in size. This list. But if you look at it, there's this antiform and there's this Eduardo fault that goes right across, and the ore bodies are asymmetric about this fault. This fault is clearly after the fault. So I think this is also post-faulting. It's not synchronous. Yet everyone they say that Rio Tinto is a synchronous. Alan Bateman, who was the editor of 50 years, said this: the sulfides are latent at both the consolidation of the porphyry and its shearing. So clearly, he thought it was very late. But now, if you talk to an economic geologist, they say it's all happening. I don't think that's right. You have to trust in the child like that one. And also, Neves Corvo is a neighbouring deposit in Portugal. It's a very large deposit. And look at the pattern there. It is located at the southern end of this anticlinorium right here. And there are thrusts and folds associated with this. And you can see that the resource itself is actually north-south trend, not along the fold axis. And there are transverse fractures that go right across the fold axis, and the mineralization is bounded against those fractures. So I can't explain this pattern in terms of a pre-fault scenario. It's very similar to what you see at Barrow, gold deposition. So Neves Corvo again is post-fold, and I think the single is also falsified in this case as well. Currawong is a special case. This is a really important deposit. This was documented by Rod Allen in the 80s. In 1992 it was published. He claimed that the massive sulfides were formed in subsea floor environment underneath the sea rather than exhalants. So this is a new idea. So we're talking about this sort of environment here instead of being exhaled. Right, so this is his cartoon of the situation. Now, if you look at the map, it looks like this. There are northeast trending folds in this area, and you get this little spot that's Currawong. That's what it looks like when you look at the dribble there. Tectonic grain is running like this. Now, I'm going to show you a movie of what this actually looks like. There are younger dikes. And can you see the pattern here again? The mineralization is asymmetric across this dike. This dike is much younger. So the mineralization has to be after the folding. This says about 2 different generations of folding. So the grade is actually traveling along the fabric, but it's terminated against the fracture that formed after the folding. So I think this model is wrong. I think the mineralization is after the folding and after the fracture. The reason that this is so important is that it's actually a foundation for hundreds of papers on subsea floor replacement. There's just 2 of them there. But it's really something like this. You know, you have to get the facts right. If your facts are not right, everything that is built upon that will crumble down. And that's the problem with this paper. So, you're going to find out what real mineral deposits really look like. Mineralization follows along local bearing formation faults. That's one thing that you saw in multiple deposits in this case.
They laterally terminate against transverse planar boundaries, like fractures. Mineralization postdates most ductile processes such as folding. This is what it looks like. This is a sample called the ruined marble from Natural History Museum. I was walking past there and I looked at it. Oh, that's a nice painting. But actually, it's a marl, and it's a marl that's inverted. This is the way up on this side. So the waters went percolating through the marl in this direction. And you can see that there are hairline fractures in it. This is the laminations, that's the stratigraphy. Okay, so that's the lamination. And these are the hairline fractures, so they're the Perkins discontinuities. So these I would call Perkins discontinuities because you have mineralization bound up against these fractures. But they are locally influenced by these laminations inside between these fractures. I terminate against those fractures. This is done. I can't change it.
Can I use your laptop?
I've got another one.
Okay. So this is what I think, this is the best representation of what mineral deposits actually look like. But that's not how most economic geologists see them as cartoons. So that's what I think. And the 125th anniversary body of economic geology is about to come out in 2030. Now, so it'll be very interesting whether the cartoon size will continue or they'll actually introduce volumes. Now, I'd like to close off this talk with this. It's been 52 years since my triumphant scientific discovery since I domesticated the butterfly. Believe it or not, this kid, who is called the 10-year-old insect professor, did exactly the same experiment that I did. And he realized that butterflies after they hatched. And he did it on these swallowtail butterflies. See? But he was a freak, like he had a whole bunch. You can look him up on YouTube. But he did actual experiments. Okay? What he did was he had these two plastic sleeves and he put sugar water on each side. And he had a lavender smell on one side. What he did was to get the cat, when he had the caterpillars, the control group, some caterpillars, he electrically shot them next to the lavender smell, not just, nothing to hurt. So what happened when they hatched the butterflies? If you observe what happened to these butterflies, you'll notice that the whole group of them would avoid the lavender smell. The train group. What is more remarkable is that he did the butterfly breeding, but he inspected the tested on the children of the adults that did the experiment. Oops, sorry. So what happened was that this trait of avoiding the lavender smell, even though the children weren't shot, they would still avoid the lavender smell. Quite remarkable. I mean, people have done experiments on other animals, so they know that this is something that happens. Now, if you are trained by a cartoon water blossom models, and your professor's saying that, okay, this, yes to the cartoon models, and you get a lot of praise and awards, and you get your honours degrees, and increase in reputation, and you get a good job, you would go to this side because you are trained to do that. If you say water blossom models, they don't make any sense. You get bullying, cancellation, people laugh at you, feel isolated, you might even lose your job. And the effect is, this is what happens. And social pressure is real. A lot of the science is actually nothing to do with science. It's to do with human behavior. But kids really don't care. So, you observe data, think, trust in each other. Thank you.
Yeah, any kind of challenges patients behavior questions. Maybe you're
No. Yes, you said that you trained your butterflies in a particular time and they did not fly. But the question that I have is
Chemistry tells you, but it must be combined with structural. That's what I do for a living. And the reason that I think a lot of these models are questionable is because academics who do this work do not look at drilling. I've modeled 1,000 deposits from all around the world. I kept on seeing this pattern over and over. It took me 20 years to figure out what the hell's going on. It's very confusing. But I think this is pretty, this is my conclusion, is that a lot of these things we are told that are genetic. I know there's a lot of publications done on it, but it's a falsifiable hypothesis. You can prove it wrong. All you have to do is get the data and just test it. That's what I'm trying to do.
Yes, I'm just wondering if anyone online wants to unmute and do the question. Meanwhile, there's.
And thank you for that very refreshing talk. I think it was great to hear that, and I certainly, and I hope many people in the audience appreciate the hypothesis testing approach. That's really important, and try and train students here to do is to falsify hypotheses. But having said that, the third step, trust in the child, is the place where I wanted to ask, I guess, a philosophical question, because trusting is not so much about hypothesis testing. There's a bit of a contradiction there. So I wonder, for the young people in the audience, what could we do differently as the next generation of geologists? These guys are the next generation of geologists. To not have to say, trust your inner child, but to test your inner child. What should we be doing? And maybe the answer is collaborating more with a variety of disciplines. But I'd love to get your view on what do we do to say, how do we test the inner child? Next generation of geologists.
How do we test the inner child?
Instead of just trusting and
Oh,
believing.
no, absolutely. I guess a lot of people are afraid of saying what they, they see an anomaly, but they're afraid to say it because it just goes against everything else that's been taught. That's all I'm saying. So being able to freely speak and say, hey, what about this? It's a really important thing to sort of have that environment. Students that they haven't been in that situation. I was very fortunate. I had 3 supervisors who were completely open with their ideas. And I was lucky, but I realized now that that's my God. Actually. But if you guys are, my boss is it's good. Good stuff.
I mean, maybe I could just be as bold as to suggest that maybe step 4 would be then to suggest to test the thing that you think.
Oh, yeah,
Things, right?
Yeah.
To go one step further and say this is the multiple hypothesis test.
Yeah.
Not just trust it, but test it.
Yeah.
The multidisciplinary way.
Yeah, totally.
Okay, Jun, I have the last 2 questions. That's
Very lovely presentation. Very nice to actually see some of the things that you share. I have a question.
Yeah.
The first comment that I have, I think the cartoon analogy develops because we needed analogs to relate to the things that we had. Limitation in terms of rate of the examples that we had. So over time, just got stuck in that well. It's moving on. So I don't think cartoons themselves are an issue. It's how we have made it over time. My question is the following: at what stage do you start using a particular framework model? Traditionally, much of the geological models are used to guide where to go for mineral deposits. Once you have discovered it, you hand it over to people who may not really care about what sort of geological model you have. So at what stage do you be having a framework to work with is very useful? When it's still at the conceptual stages, it's a continuous thing that you build as you continue to mine.
Geological model. My belief in the geological modeling process is repeatable. One of the things that in the Parker Challenge, they gave a data set to 20 resource professionals. And the variety of models was plus or minus 200%. After taking out the outliers, that is not an experiment that's repeatable. You know what I mean? So I think it needs to be very specific. Otherwise, it's just a sketch. That's the problem with geology. Is that there are infinite ways to model geology. So we need to come up with a scheme that everyone can repeat.
Just to add to that, if you meet a junior mining company nowadays, they will tell you we're looking for IOCG deposit because they have a conceptual.
Oh, yeah, okay, yeah.
So I'm talking about that.
Theoretically.
Exactly, because if you say the so-called VMS deposit model, they are all epigenetic deposits, it changes the framework of what I'm looking for.
Oh, absolutely, yeah, yeah, it does.
So at what stage, because we have very limited information in this field, to
Well,
say that all the things that we made an assumption of to be like this, globally, we have a population that actually shows that it's the focus.
yeah, I think you need to change the strategy when you start to waste too much money. I mean, this is a situation where I went and studied a nickel sulfide deposit. This company had an ultramafic unit. They were drilling to the back. And there was nothing. They kept on drilling. They kept drilling. But they had an ore deposit that was right next to the ultramafic unit in the turbidite football sequence, not even in the ultramafic. And they were mining. Now, to me, it doesn't make any sense. The model is wrong. model is so strong. We are told that this is right. People do not question them. So I guess I have an easy time questioning because I see patterns that just do not fit the models. But a lot of people have a hard time changing them. That's a psychological issue. It's not a science issue.
Yeah, no, I agree.
Yeah.
And your last one, Sue, are you still in your question?
Yeah, I was just going to say that I agree with everything you say about models and that the genetic theory is very dodgy. But I do believe that what we actually saw this morning in your course was basically that you get a lot of mineralization in fold closures and along fold axes.
Yeah.
So slowly post-genetic deformation, later deformation, can very easily concentrate your mineralization, but then be cut off by these Perkins limitation or almost at the same time.
It could be, yeah, that's another model that should be tested. Yeah. But I still think the majority of those actually the discontinuities came after the fold. It's very difficult.
After the fold.
Especially if folding is isolated. Those planar boundaries.
So do you believe that the mineralization came into those fold closures later?
Yeah.
Okay. Yeah.
Thank you very much. Thank you all to the audience. And thank you to June to actually come and visit us a bit. It was a privilege to spend so much time with you and learn from you and learn from each other. Your starting work which make you travel again to Europe. And next year to the World Conference. So thank you very much and see you next time.